Okay, let's go. It's my pleasure to introduce Jorge Alda, a young researcher from the Universidad de Zaragoza, who is about to defend his PhD, I think in a couple of months, under the direction of Siena Peñaranda. And today is going to talk about machine learning techniques applied to flavor physics phenomenology. Jorge, go ahead whenever you want.
Okay, thank you. As Ernesto said, I'm going to talk about the use of machine learning techniques in phenomenological studies of flavor physics. This is a work that I have done in collaboration with Siena Peñaranda from Zaragoza and Jaume Walsh from Barcelona. Has been uploaded to the archive in this. So we are interested in studying the anomalies that are a series of experimental results in the case of B mesons that they don't conform with the prediction of the standard model. In particular, they show some hints of violation of the universality of the electronic statement. That is a property predicted by the standard model. The first kind of B anomaly that we where a big quark decays into a quark and a pair of charged electrons, where later electron and a muon. That the smoking gun for the anomalies are the LK and LK star observables that are constructed as a ratio of Brainfield ratios for the case into the muon mode or the electron mode. Taking the ratio cancels out the hadronic uncertainties, so this observable it is predicted to be 1 at a per mil precision. But the experimental results in LHCb and also in Bell have shown a deviation from this one, and in particular for the charge decay is 0.846, and for the neutral Coulomb star is 0.685. Taken together, this is a tension of 3.1. There are also related anomalous results in the angular distribution of the decay into the vector count measured with the observables P4 prime and P5 prime, and also in the case of the DS meson into a free meson and a pair of modes. The second kind of anomalies that we are going to study occur in the charged processes where a B quark decays into a C quark and a charged lepton and a neutrino. In this case, we take also a ratio between the tau mode and a light quark mode. This is either a muon or a average of electron and muon. Here in this plot in the right, we have the situation of this kind of decay where the ellipse here in the horizontal axis for RD and the vertical for RD star. We have, and this red is the combination of this red region, the combination of all experimental data at 1 sigma, and the dashes contour is the same but at 3 sigma. And here, this cross here marks the standard model prediction. We see that again the experimental results are 3 sigma away from the standard model prediction. And there are also other related anomalies in the polarization of the D star, for instance, in this case, and also in the case of the BC decaying into a Jepside meson and a left-hand image. Okay, the tool that we are going to use to characterize and describe this kind of anomalies are effective field theory. That is a way to describe the deviation from the standard model in a model-independent way. And that is using effective operators constructed with the field of the standard model, but with dimension greater than 4. And we have this kind of Lagrangian with these are the operators, and the numbers that multiply them are the Wilson coefficients that encode the dynamics of the highest scale. We are going to work at an energy scale lambda that is above the electroweak scale. And in this case, the standard model specific that has 2,500 operators. We will focus on operators of this type on this type, or LQ1, where we have a electronic current and a quark current coupled as a singlet, SU2 singlet, and LQ3, where the electronic current and the quark current are coupled as a triplet. This is described of the neutral current, and this was the neutral and the chance. But that was at the high scale lambda, where we expected any kind of new physics, but the case of the B mesons occur at a lower scale, at the scale of the mass of the B quark. And at this energy scale, we have to integrate out, apart from the new physics particles, also the heavy particles of the standard model, the top quark, the Higgs, and the double heavy degrees of freedom. We obtain the weak effective theory, and the operators of the weak effective theory that are relevant for us are these ones here, O9 and O10, that are the ones that affect the RK and RK star ratio, OBL, that are the ones that affect RD and RD star, and also we are going to consider the decays of the mesons into a count and a pair of nature. This will be important for our work. So we have to implement a way to translate from the higher scale physics in the SMEFT theory to the low energy physics in the web. This is done with the procedure of scale lambda down to the electroweak scale, then matching the both effective theories, and then running down to the scale of the B quark. So doing this, we obtain a set of matching conditions between the wet operators here and the SMEFT operators. In black, we have the two levels relation, and in blue, we have a loop level correction. For the C9 operator, that is different from that it is present in C10, and that is a universal correction. It doesn't depend on the flavor of the quark, of the electron. But at the level, C9 is equal to minus C10, and this is a feature of many proposals of models of new physics. But this creation is broken by the one loop correction. Okay, the settings that we are using for our work was proposed first by the Padova group, by Ferruccio, by the Parisi, Andrea Patori, and this is the idea is to consider that at the higher scale there are some interactions that affect only to the third generation quarks and leptons. And this is encoded in this LQ1 and LQ3 that affect interaction basis. And we then have to rotate back to the basis of mass eigenstates that are the physical particles that we see. And this is done with two rotation matrices. One for to rotate the leptons, that is lambda L, and one to rotate the quarks, that is lambda Q. These rotation matrices must be Hermitian, idempotent, and with size equal to 1. And it can be parameters because I just forgot that are alpha and beta. We have alpha and beta for lepton and different alpha and beta for both. Here, the elements on the diagonal describe alpha square and beta square describe a direction of Lepton Flavour Universality, that is that couplings that are different for the different flavors of the fermions, and the off diagonal describe a relation of Lepton flavor. That is, for example, a quark, a tau lepton decaying into 3 muons, or decaying into a muon and a photon. Here we have, in principle, C1 and C3 can be independent from each other, and we will require that to cancel out this term at 3 level that causes a large division in the case of the meson decay into alpha and a pair of each. This structure of rotation matrices causes a bit of trouble in the first place, because as I have explained, it introduces a source of Lepton Flavour at the high scale. We have to run the renormalization group equations, and this causes a mixing between different operators. Not only the CLQ operators that we have introduced at the lambda equals to 1/10, but also different operators, for example, operators involving the Higgs quark and a pair of leptons that modify the coupling of the zeta, the CS boson to a pair. And these are keep everything in check. We have to use to analyze not only the B anomalies, but also a wide range of observables that are experimentally measured. And this is done through a global fit. To do this global fit, we have used Python 3, and we have 3 different Python packages. The first one is Wilson, that is the one responsible the question and the mixing of the different Wilson coefficients. Then Flavio, that is used to calculate the observables in the different effective theories, and also has used a database of experimental measurements. And the third one is SMEFT, that is the one that implements the likelihood function, that is the thing that we minimize to obtain the result. And this likelihood function is approximately equal to the chi-square difference of the experimental values for the different observables minus the theoretical prediction weighted by the covariance matrix. This matrix has also experimental and theoretical components, and in general it's a block diagonal, so we can work a block diagonal. For our global fit, we have used new decay, but also electroweak observables, nuclear beta decays, Lepton Flavour violation observables. So we have a constraints for everything that we need. And we consider two different scenarios. The scenario one that was the one proposed by the Padova group. They assume that the mixing to the first generation eligible, and they only consider that any physics can mix the third and the second generation. But we also consider a marginal scenario where the mixing can occur both for the second and the first generation. So these are the results of our fit. We obtain a significance of between 5 and 6 sigma. So we encountered something that was at first suppressed. That is the beta L, that is the mixing to the second generation of leptons, is compatible with 0 for our L3. And this is suppressed because we are studying the RK observables that are decays into muons. So we would expect that in physics would appear in muons. So what's going on? You equal the likelihood is here for the mixing in the leptons, and here for the mixing in the quark. And this plot here is the one interesting because here alpha X, that is the parameter for the mixing of to the first generation of leptons, is constrained by these red lines that are the fit to the RK and RK stars. But beta these green lines that are that come from Lepton Flavour violating. So Lepton Flavour violation, for example, a tau decay into a muons or tau decay into a muon and a photon, is what limits the direct impact of new physics in the muons. So how does this look for the we have on the left the situation for RK and the right for the RK. In blue we have the results of our fits to both scenarios with their error bar plus sigma. In yellow we have the standard model prediction. The dashed line is the central value, and the colored region is the 1 sigma prediction. And for the RDE and RD star case, our fit reproduces quite well the experimental. Here for RK, we have that scenario 1, that is the circle. The predictions are all of them equal to the prediction of the standard model. But scenario 2, that is when we add the RK a value that is perfectly compatible with the experimental result, and for RK star we have a value that is compatible at 2 sigma, and that is a significant improvement with respect to the standard model. So what is going on? The fact that beta L is equal to 0 implies that C10, which is directly proportional to beta L, also has to be equal to 0 for the muon. C9 to the most only has the universal contribution that comes from the one loop correction. In scenario 1, we are forcing by hand that alpha L is also equal to 0. So in scenario 1, C10 for the electrons is also equal to 0, and C9 for the electrons is also only the universal part. So in scenario 1, basically we have the same mean physics contribution to the electron out, and the ratio is again equal to 1. But once that we add that we allow mean physics to affect also alpha L to affect the fertilization, we have for the muon we have the same as before, but for the electron we have a three-level contribution to C10, that is here, a three contribution to C9 for the electron, that is the value for the C10, and the value for the C9 for the electron is different to those for the muon. So we can have a breakdown that is different for different than the standard molecule. That is the one that we have. So with this we have more or less understood the best fit point, but we are so this of the likelihood function in an area around the best fit point. The problem is that each point of the parameter space, that is a 5-dimensional space, requires a calculation of almost 500 observables, and the calculation of many of them requires numerical integration that takes something. In a previous work, we used using the second order Taylor expansion. The first term is equal to 0 because we are around the minimum of the function, and the second second order gave us a good enough approximation of the likelihood. But in this case, this approximation is not very useful because we have here that the region of a constant likelihood from the disease. So this we would need to add more terms to this expression, and more terms becomes difficult to calculate. So the idea was, instead of approximating this by a series expansion, was to teach an algorithm, a machine, some way to reproduce this likelihood function in computationally expensive way. So we use the XGBoost algorithm that is based on a regression tree. So the basis from a regression tree is a decision tree, that is a set of branches and nodes, and in each node, depending on the value of one of the input parameters, it goes to another, some branch or to another, and that classifies each point in categories. Then a regression tree is a modification of a decision tree where each category of the, is associated with a real number. So we can see a regression tree as a function that goes from the space of parameter points, in this case from C alpha L, alpha Q, beta L, and beta Q, to the real number. So, but a single tree is not good enough to reproduce an arbitrary function. So, and sometimes together, we have a function produce a near recursive. So the Higgs algorithm is called extreme gradient boosting. The idea is that we have a set of X points that in our case are that C alpha L alpha Q, beta L and beta Q, and a set of and the corresponding good at this point, and we want to find a function phi that so that when evaluated in the X point, it gives us an approximation of the Y. So in order to quantify the goodness of the phi function, the algorithm defines a regularity objective that is in our case a mean absolute error that measures how different are the approximation from the real values, and then a function omega that penalizes the complexity of the trees. For example, it penalizes trees with many branches or trees where the values of the branches are too high. So this regularity this objective iterative way. So there was it starts with a simple tree with only one branch, so only one leaf, and at each step only has to ensemble the tree with one more branch that optimize locally this likelihood. And in order to prevent overfitting, that the algorithm learns only these points, but is not able to extrapolate the points. Leaves are multiplied by a parameter eta that is analogous to a learning rate, and this process is called shrinking. So we have used a sample composed by 10,000 points. Half of them come from the elaboration of the plots that I showed before, that are recycled points, and the other half were computed random points around the best fit area. And we split this sample in a training set and a value set. So these are the results as seen in the validation set. We have here the regression between the actual values of the likelihood for the chi-square, and the predicted values by the algorithm. We obtain a good agreement between the actual values and the predicted values with a regression coefficient of 0.97 and a mean error of 0.65. So we have an approximation for the likelihood function that can be evaluated in a very short time. So in order to explore the area around the best fit, we want to generate new points that are distributed according to the probability distribution given by the chi-square. So the way to do this is with a Montecarlo algorithm, where each proposed point is accepted or rejected with according to a random number is related to the ratio of probabilities. So in our case, what is here is very expensive, and especially if we take in account that most of the points are going to be rejected. So instead of using a true likelihood function, we use for the Montecarlo algorithm the approximation that we have obtained with the machine learning algorithm. Here we see the result. Here, interest is the chi-square distribution, and in blue is this one. So now that we have an approximation of based in a machine learning model, we want to understand what the machine learning does, and this can be done with the SHAP values that are a measurement of the importance of each parameter in the prediction for each data. Sorry, and the properties of the SHAP values is that the sum of all of them plus a constant value has to be the prediction of the machine learning algorithm. That if some of the parameters missing, the SHAP value has to be 0, and that if we change the model so one parameter becomes more important, it is a measure of how relevant, how important is each parameter. The idea behind this is that if we have one model and one machine learning model with the n parameters, we train to the n simplified model where some of the variables are missing. So for example, here we have the arithmetic mean of the prediction. Here we have models with just one parameter. Here models with 2 parameters, and here the model with 2 parameters. And we can measure the marginal contribution, that is how one single parameter contributes to the prediction by taking the difference between see how the contribution of the first of x1, we can take the difference between here and here. That is something that depends on x1, something that doesn't depend on x1. Also, the difference between here and here, that depends on x1 and x2, and here it depends only on x2. The difference between here and here, this depends on x1 and here, because this depends on x1, x2, and x3, and this depends only on x2 and x3. And this gives us the marginal contribution. If we take an average of all these marginal contributions, we have the total contribution of the parameters 1 to the final prediction. And we can do the same for x2 by taking the difference marked with green lines here, marked in with the blue lines here, and this is the idea behind the SHAP value. In practice, the algorithm doesn't need to train the different models. This can be done with the information contained just in the total model, and in particular, if the machine learning model is based on a tree, for example, in our case, very efficient and can be in polynomial. So we here have the SHAP values for the different parameters of our fit, calculated in the sample of points generated by the Montecarlo algorithm. We see that according to this SHAP value, the two parameters that are the most important are beta q and alpha L. Beta q is the parameter that since we are studying decays into from B to C and from B to S, this is natural to be important. And also we have alpha L, that is the one control in the mixing to the lepton in the first generation. And as we have seen before, this is the one responsible for the explanation of RK and RK star at the value level. And we see in detail the visibility point. We see that the value of C that controls the overall size of the new physics is also very important for the final answer. And here we have a comparison between the SHAP values as a function of the parameters of the field, here as a function of C, as a function of alpha L, and as a function of beta L. But we have the logarithm of the likelihood also as a function of the same parameters. We see that there is a general agreement between the two of them. For example, here we will have to take the negative here because we are minimizing this. So, but here we have the minimum of C for minima for alpha L correspond to the two maxima for the SHAP value for alpha L, and the minima for beta q corresponds to the maxima of beta q, and the slope here corresponds to this. So the SHAP values are more or less follow the overall shape of the likelihood. So this is next. Study correlation between the different Wilson coefficient of the weak effective field theory, also in the data set that we have generated with the Montecarlo algorithm. Here we have first we have something that was expected, that is for example 3 blocks of values that are highly corrected. That's this here, and this here. For the electron, CPL for the electron, and CNU for the electron, for example, they all depend on the same factor of parameters. This C10 for the muons, CPL for the muons, and CNU for the muons also depend on a different combination of the parameters. So they are all correlated. And here we have a CPL for the taus and CNU for the taus that are more or less expected. But we also have something that is unexpected or not so bad. Here C9 for the muons, that it has a very low correlation with the rest of the muon coefficient, but it has a almost perfect correlation with the tau coefficient. And this is because, as we have seen before, C9 for the muons is generated exclusively by the loop contribution. That loop contribution is flavor universal, and doesn't depend of the mixing for the lepton homogenation. So it depends on this combination. And this is approximately equal to here, to this here, because lambda L for the third generation is equal to 1. So we have this correlation. And then we have a C9 for the electron. First, with the electron sector, with a correlation of about 0.65, and also a similar correlation to the tau sector. And this is because C9 for the electron has two contributions of similar size, one from the tree level and one from the loop level. And the tree level contribution, it depends on the same parameters that the electron, then the rest of the electron coefficient, and the loop level contribution is also a favorite universal, so it is the same as the tau and the C9. So these correlations are in agreement with the renormalization group equation that we have seen before. So this is a check, a sanity check. And here we have also in the sample of the Montecarlo pointers that we have generated with the machine learning algorithm, the correlation between observable we have sectors to see if there are some notable correlations. So the first thing that we notice is that RK and RK star are not very much correlated with the decay for the BS meson into a pair of nodes. And this is important because many models of new physics do predict this kind of relation. And as decay into modes is mediated by the C10 coefficient that in our case is not related to the C. It's not correlated to C. That is the one that dominates RK and RK. We also have a moderate correlation between RK and RT that is in contrast with some other proposals that predict this apart. In our case, the RK and RD don't have a really simple explanation simultaneously for them. And finally, we have here a perfect correlation between RD and the decay of the meson into a count and a pair of neutrinos. And this is because both of them depend on the tau coefficient that CBL tau for the RT case and CB tau for the meson decay into a pair of neutrinos. And we are going here in a moment to comment that. And finally, we see that there is no single observable that displays a large correlation with the total likelihood. And this is an indication that we have to consider all of the operators, not just all of the observables, not just one or two, because otherwise we are not seeing the whole picture. So here we have in more detail the correlation between RD and the decays of the meson to a count and a pair of neutrinos. Here the blue points are the correspond to the Montecarlo points that we have generated, the values of RD and the registration, with the cross marking the values at the residue. And we see that here in yellow we have the standard model prediction for the neutrino decay, and in green we have the experimental measurement for RD. And we see that a deviation in RD from the standard model that to be from here. In our setting implies also an excess on the neutrino. We have here in red the excluded regions by experiment. So we see that after there is an excess, it doesn't cross into the tangent zone, into the excluded region. So everything is fine. But if we consider C1 and C3 as independent parameters, we would have crossed to this region. So this is equal. And finally, the most interesting part is this gray band. That is a result by Bell2 that was published a bit after we did our numerical analysis. And Bell2 found a deviation from the standard model. There is still much uncertainty, so this is not an anomaly. And the interesting part is that this Bell2 data is not included in our field. So we have seen an excess deviation that is more or less compatible with the experimental data before the experimental data was free. So this is an indication that our idea for the correlation between RD and P to count and 2 months might be something behind it. To conclude, we have worked everything in the effective field theory formally, but we would like to express our results in a way that is compatible with a specific model of physics. We have chosen the leptoquark, and in particular the vector leptoquark U1. That is a leptoquark is a particle, an hypothetical particle that decays into a quark and a lepton. And this one quarks or into two right-handed, two left-handed fermions, sorry, or two right-handed fermions. The matching between the leptoquarks and the SMEFT operators is given by this expression. And in our case, since we don't have right-handed particles in our, we only have this expression. From here, we can in terms of the parameters of our field. And for our scenario 2, where we consider both mixing to the first and the second generation, we obtain this coupling here for the lepton. In this third column, we have XL23 and XL23 that are the couples to a tau lepton and the second and third generation quark that have been proposed as a solution for the RB and RB star anomaly. And the values that we find are compatible with the spinal density. But here in the first column of the coupling, we have also two values that are different from zero that correspond to the couplings to an electron and a second generation quark, or an electron and a third generation. And these couplings here that were not proposed previously are case started. So we have this part for the RD and RD star, and this part for the RK and RK. So all in just one new particle that would be the leptoquark. We also have tried some different models, for example, W prime or Z prime bosons, or other leptoquarks, S3 scalar leptoquark, for example, but values for the LQ1 and the LQ3 operators. So in our case, they would produce a large deviation in the production of neutrinos that are not compatible with experimental. So we only consider the one leptoquark. So to sum up, we have seen that we can use the effective field theories to describe a setting where RD was generated at level, and RK was the result of the interplay between level effects and loop levels. We have used global fits because they are needed to take into account several side effects in other kinds of observables that are not the anomaly. We have seen a machine learning model that is able to approximate the likelihood function. We have used the SHAP values we have found an interesting correlation between RD and the decays of B meson into counts and to neutrinos. And we have shown an explanation of this new physics described by the theory in terms of a new particle that is a leptoquark, vector leptoquark U1 that couples to the third generation of quarks and the third generation of leptons for the case of RD, or to the first generation of leptons for the case of RD. So this is with this I conclude the talk.
Okay, thank you very much, Jorge. Very nice presentation and seminar. It's time for questions, comments. Sabas, go ahead.
No, I was just clapping. Yeah, sorry.
Okay, sorry. Juan Antonio.
I can hear.
No. We can hear Juan Antonio. No. Are you there, Juan Antonio?
A table with a lot of coefficients. But 5,000 points seem too little, right? To parameterize a 5-dimensional space.
No, 10,000 is some of this and this.
Well, then, I mean, the fifth root of 10,000 is like what? Let me have a look. 4. I mean, you have 4 points for each dimension. I think it's too small. Besides that, you are interested most in the region where the chi-square is small. I mean, you have a perfect correlation in that curve, in that scatter plot, at a high chi.
No, but this is the chi-square. Yeah, we are interested in this region where the chi-square is high.
But if you are doing, you mentioned you were interested in the region close to the region of the minimum chi-square, right?
No, in the minimum of the likelihood, but there is a minus sign here. So the minimum of the likelihood corresponds to the maximum of the chi-square. So.
Okay, no, then probably it's not so bad. Okay. I misread it. I thought you were in the other region when you have a bad correlation.
No, I'm here in the region with the correlation.
Okay. And then I think it's fine. Okay. So that's all. Thanks.
More questions, comments? Okay, I have one. In order to measure the feature importance, you have used the SHAP method, but I think the XGBoost tool has a method to measure the importance of the feature that is called a score. Have you compared both methods? Are similar or the same?
No, I didn't compare.
Sorry, Jorge?
No, that I didn't do the comparison between.
Okay, because I think it's interesting to see how dependent the results are on this method to measure the importance. I think maybe you can you can check that.
Okay, I'll look into it.
Okay.
I have one question.
Okay, go ahead, Maria Jose.
Have you finished? Sorry, Ernesto, have you finished your question?
Yes, Maria Jose, go ahead.
No, I mean, I don't know anything about machine learning, so my question is very naive and is regarding physics. From the kind of way you study this, which is interesting anyway, can we learn more about the physical interpretation of the anomalies? In other words, have you compared different cases, not only leptoquarks, but other possibilities, and from the way you study the problem, have you concluded that one hypothesis favors the others, like, you know, leptoquarks versus something else?
We only consider in depth this vector leptoquark because this is the one that generates this relation between the LQ1 and LQ3 that keeps in check the decays into the neutrinos.
So you conclude that the leptoquarks apparently explain relatively well.
Yeah, they could work. We look into W prime or zeta prime or other leptoquarks, for example, scalar leptoquarks, and they didn't have this relation here. So this has the potential trouble of this kind of processes, but we didn't look into it with much details. Only
would be interesting
exploratory
to benefit from the new approach that you use, the machine learning, as to improve the comparison with underlying ultraviolet theories, for instance. Not only leptoquarks, but others. And that probably the way you deal with the issue with this machine learning will give you more information than other ways.
Yeah, I mean, machine learning was really just a way to speed up the computation to make things easier. But machine learning doesn't give any additional physical insight that we don't have with the others. So.
But the study of the correlations, I find it particularly interesting that you are showing in these slides. So yeah. This kind of way of approaching to the issue, I mean, looking for correlations among, on one hand, the coefficients and on the other hand, observables, I think should be more studied more frequently. Once you assume a particular underlying theory that provides to you the set of coefficients, whatever, and that should be systematized, como se diga.
Yeah.
Okay.
Yeah.
Thank you for the seminar. Nice.
Thank you.
Final comments. Rosa, go ahead.
Yes, thank you. Very nice talk, first of all.
Thank you.
I want to ask if you make any kind of data preprocessing before before applying your regressor. Do you know if any feature is more important than others, or have you tried any other kind of data preprocessing to improve your performance?
Well, the only thing that we did here is to consider only the points with the chi-square greater than 20. Because we rejected the points with lower chi-square, but it was just that. Nothing.
Okay, thank you.
I think it's time for more questions or comments. No? Okay. Then let's thank Jorge again for the nice talk. And I think we can finish here. Bye.
Bye.